Let's continue the thought process on the process of equatorial trapping and its relation to the induced vorticity. We did the case of the basic state being stationary. We'll now move on to basic states with constant U and then add meridional shear. Remembering our section of the fluid we are looking at, this is the latitudinal direction. We have this is the mean height, and then you have a sloping deviation from the mean height if you want meridionally sloping pressure gradient balancing the zonal geostrophic wind or current. And then there is either a rigid lid or there is a free surface given by this small h varying in lambda, phi, and t. Since in this case u bar is constant, we can integrate this equation in y and end up with an expression for the deviation from the mean height for this slope we need to drive geostrophic currents. So Hs is then written as minus beta y squared u bar over 2g. So you integrate these both sides and you get y squared over 2g and Hs. That's fairly straightforward. Since u bar is constant, du bar dy is 0, so there is no basic state relative vorticity. So the relative vorticity doesn't have any basics. That doesn't have any relative vorticity. Then the induced vorticity can be written as we did before in terms of the Hs0 at the trapping latitude and Hs and the mean height. So we are going to look for how the change in induced vorticity occurs when you have a easterly or a westerly western state compared to the basic state, which is stationary, right? So you look at Hs as minus beta y squared u bar over 2g that we just derived, plug it into this induced vorticity equation. We are going to end up with this expression with u bar term in the denominator and the numerator. So we are basically going to see whether u bar term makes this smaller or larger, so that induced vorticity is smaller or larger based on the background state or the basic state, right? It's fairly straightforward derivation when there is a displacement of the fluid column in the meridional direction, and there is scale of the mean depth and the horizontal scales involved as before. So that we end up getting induced vorticity for easterly flow having lower vorticity than the stationary state, which itself is less than the westerly basic state. So this has greater trapping, which means the turning latitude is closer to the equator compared to either the stationary basic state or the westerly basic state. We are saying the same thing as we did before, but we are now arguing in terms of induced vorticities, because we will soon say that exponential decay of the induced vorticity is the process that is causing the trapping, and its scale depends on the various factors we have looked at in terms of beta, mean depth, horizontal scale of motion, and basic state, right? So we can summarize it in this way. If we have a normalized restoring force that is either the beta or mean depth and so on, Hs bar sloping, etc. So if you have a non-divergent motionless basic state, so the surface height is in that case constant, and you displace the column, fluid column, in the direction of a smaller h. We'll see that later on. In general, this turns out to be naturally so in the ocean and the atmosphere, because the troposphere, for tropopause itself, is decreasing from the tropics to the higher latitudes, for example, and in the ocean you can think of it as columns moving parallel to the rotation axis on the sphere. So we'll see some figures that will make it clear. So if you have a stationary state, then you have non-divergent flow, then there is no trapping. The solution induced vorticity will go all the way to the poles. If you have a divergent motionless basic state, in which case there is no rigid lid, so you have you allow for free surface for the geopotential, in which case you have a moderate trapping. So then the induced vorticity drops off to the trapping latitude. If there is a westerly basic state and it has divergent flow, then again you have free surface tilt. Induced vorticity now is going to be also dropping off, but the trapping is weaker because this induced vorticity is greater than this one, which is greater than this one. At least, well, I shouldn't say greater than this one, but we know what you mean. Okay, this is smaller than this one, which is smaller than this one. Okay, divergent easterly basic state. So instead of westerly basic state, we have an easterly basic state. So now you require the slope to be the other way. So when there is no basic state, there is no HS, there is no slope needed. Whereas when you have easterly or westerly flow, the slope changes. So in this easterly case, the HS increases towards higher latitudes, whereas here it decreases. So here you have a westerly easterly basic state, so the trapping is stronger, which means the vorticity, induced vorticity, drops off much faster. So the flow is the flow is trapped to the equator, waves are trapped to the equator much more strongly. It's the same story. Shear flow, you set u bar as a function of y. It's not constant, in which case now you have slope required for the sheared flow is greater than for the non-sheared flow. So if you want to vary u in the meridional direction, either as a easterly or as a westerly, then you need greater slope. So that's the same story, in which case we can state overall that the decrease of relative vorticity, induced relative vorticity with latitude, is essentially the first order explanation for the mechanism of trapping equatorial Rossby waves. In an easterly flow, as we saw, the effect of beta is reduced, leading to a more rapid decrease of zeta. What are we saying? We said before that beta effect is the restoring force, right? That's what keeps the equatorial trapping and gives you the vorticity dynamics. That's the planetary vorticity gradient. So when you displace a column, you're going to introduce relative vorticity. You're going to induce relative vorticity. So the easterly flow essentially weakens the beta effect and provides a greater tapping of the ER about the equator, and the westerly flow will work the other way and reduce the trapping. So when you say reduce the trapping, you have to be sure you understand. Stronger trapping means closer turning latitudes. Weaker trapping means further away are the trapping latitudes. And that corresponds to the E-folding depth of the induced vorticity. So different ways of saying these. These matter because we will see later on that as we move the air columns in the tropical dynamics, we will invoke these basic mechanisms we are learning by using simple easterly, westerly, and sheared flows, and looking at the impact of horizontal and vertical scales, mean depth and L, right?